So let's start today's lesson. We're continuing from where we stopped yesterday. Yesterday we had just looked at what is rules of inference. We looked at some examples for modus ponens. I just want to recap on what the rules of inferences are because we're going to look at examples, and based on these rules of inferences we're going to do some examples and problems today. Okay, so yesterday we had already seen modus ponens. In modus ponens, what we are saying is that if P is true and P implies Q is true, then Q is true. That is modus ponens. Okay, whereas if we are saying not Q is true and P implies Q is true, then not P is true. This is called modus tollens. Okay, then we have hypothetical syllogism, where if P implies Q is true and Q implies R is true, then P implies R is true. This is hypothetical syllogism. Okay, now if we have P or Q is true and not P is true, this implies that Q is true. Okay, because see, if you look at it itself, we know P or Q means either P must be true or Q must be true. But in the second statement, we are saying not P is also true. Okay, so not P is also true means whether the P's value is true or false does not matter. So if this has to be true, then Q has to be true. If both these statements have to be true, then it's possible only with Q being true. Okay, so this is called disjunctive syllogism. Okay, then we have addition. If P is true, then P or Q will be true. Obviously, because any one needs to be true for P or Q to be true. Now, simplification, if P and Q is true, that means both P is true and Q is true. So that implies P is true. Okay, that is called simplification. Okay, now if we look at P is true separately and Q is true separately, that implies that P and Q is true. Okay, because both are true. Then we have resolution. This is important because this we'll be looking at separately also. We saw it earlier also. Now, P or Q is true. So either P or Q is true. And not P or R is true. So either not P is true or R is true. Okay, but if you see over here, P cannot be true and not P cannot be true. That is, true and false cannot be the same value. So actually, if all these should be true, that means P or Q should be true and not P or R should be true. Q or R should be true. This is called resolution. Okay, and this is important. We'll be looking at it separately. Okay, now let's move on to the examples. State which rule of reference. Look at this and tell me which is the rule of reference. We saw that only P is given to us. That there are only two in rule of inference with just one premise. Okay, that is either the addition or the simplification. All others have two premises. Okay, so this one is the addition form. Okay, that the statement, you can read the statement with state which rule of inference is the basis of the following argument. It is below freezing now. That is P. It is below freezing is P. It is below freezing or raining now is of the form P or Q. Okay, so this is of the argument form addition. Now look at this statement. It is below freezing and raining now. Therefore, it is below freezing now. So we have a single premise P or Q. Sorry, P and Q. And then it implies P. So this is of the form simplification. Okay. Now we have the statement here. If it rains today, then we will not have a barbecue today. So this is P implies Q. If we do not have a barbecue today, then we will have a barbecue tomorrow. This is Q implies R. Therefore, if it rains today, then we will have a barbecue tomorrow. So the conclusion is of the form P implies R. And this is hypothetical syllogism. P implies Q, Q implies R, concludes that the conclusion is that P implies R. This is hypothetical syllogism. Okay, this is where the whole lesson was progressing towards how to build arguments, how to show that something is true or prove that something is a hypothesis is valid. Okay, the rules of inferences allows us to build valid arguments. Now we're going to look at examples. Show that the premise is it is not sunny this afternoon and it is colder than yesterday. That is one premise. We will go swimming only if it is sunny. This is premise 2. If we do not go swimming, then we will take a canoe trip. This is premise 3. And if we take a canoe trip, then we will be home by sunset. This is the fourth premise. So we have got 4 premises, and where it's saying that it leads to the conclusion, we will be home by sunset. Okay, let's see whether this argument is valid. Okay, so first let's write the prepositional statements. Okay, let P be, look at these statements and decide how you're going to write the prepositional statements. It is not sunny this afternoon. That is a statement. Okay, so instead of having the negative, we will say, let P be, it is sunny this afternoon. And to represent the premise, we will use not P. Okay, and we have another statement, it is colder than yesterday. That will be, let that be preposition Q. Then we have the statement, we will go swimming. Okay, let that be preposition R. We already said that it is sunny, so we don't need to represent this part of the premise here. We have already represented it using P. Okay, if we do not go swimming also, we have represented it using the R. Sorry, R. We will go swimming. So then we don't need to use, for the third premise, we don't need to have the first part. But we will take a canoe trip. That is another premise. So now we've got P, Q, R. So S will be the proposition. We will take a canoe trip. Okay, and then for the fourth premise, if we take a canoe trip, that's already there. We will be home by sunset. Let it be the next proposition T. Okay, we will be home by sunset will be the next proposition T. And the conclusion is we will be home by sunset, which is T. So we don't need to represent it again. So now we have got the propositions P, Q, R, S, and T. So the first premise can be represented as not P and Q. Okay, the second premise can be represented as R implies P. Okay, the third premise is not R implies S. And the fourth premise is S implies T. So from these 4 premises, now we don't need to look at the statements. We have converted the English statements into prepositional logic. Now we need to check whether these 4 premises gives the conclusion T. Okay, so we need to, this is the reasoning. And in this reasoning, I'm using simplification, modus ponens, and modus tollens. So whatever we are using over here, I have just copied it and pasted it on top so that I don't have to flip through the slides. Okay, so we are going to begin with the first premise, not P and Q. Okay, so the premise not P and Q. When we use simplification, if it is not P and Q, P and Q implies P. So when we use simplification from 1, we get not P. Okay, then we are taking the second premise, R implies P. Okay, so we are taking the second premise, R implies P, and when we take both 2 and 3, look at modus tollens. Not Q and P implies Q concludes not P. So we have not P and R implies P. So the conclusion is not R using modus tollens. Okay. Now let's take the next premise, which is the next premise. Sorry. Here, not R implies S. Okay. So now we have got not R and not R implies S. This is of the form P and P implies Q. Okay. This is modus ponens. So modus ponens, when there is P is true and P implies Q is true, then Q is true. Okay. So here not R and not R implies S implies that S is true based on modus ponens. Okay. So now we take the next premise, S implies T, which is the last premise. Okay. So from the conclusion S and S implies T, again this is modus ponens. It concludes that T is true. And that was our conclusion. Okay, sorry, back. Sorry. Here, the conclusion was T. So from these 4 premises and using the rules of inferences that we have already learned, we can conclude that T is true. So we will be home by sunset is a true conclusion. The conclusion is valid. We cannot say it's a true conclusion. We have to say that the arguments are valid, so the conclusion is valid. Okay, now let's look at another example. Show that the premise is, if you send me an email message, then I will finish writing the program, is the first premise. If you do not send me an email message, then I will go to sleep early, second premise. And if I go to sleep early, then I will wake up feeling refreshed, third premise. There are 3 premises lead to the conclusion, if I do not finish writing the program, then I will wake up feeling refreshed. Okay, so now let's convert these statements into propositional logic and premises and conclusion. Okay, now let's look at the first statement. If you send me an email message, okay, so let P be you send me an email message. Okay, and let Q be I will finish writing the program. Okay, the first part of the second premise is just the negative of P. So this we don't need to represent again. So let R be I will go to sleep early. Okay, then first part is the same as R, so no need to represent it in the third premise. In the second part of the third premise, I will wake up feeling refreshed. Let that be the proposition S. Now we have got all the pieces. Let's write the propositional statements of the premises. If you send me an email message, then I will finish writing the program is P implies Q. Okay. Second premise is not P implies R. And the third premise is R implies S. And the conclusion is, if I do not finish writing the program, that is not Q implies S. I will wake up feeling refreshed. Okay, now don't look at the English statements. Instead, look at the premises and the conclusion only. Take each premise and see whether you can use one of the rules of inferences to come to the conclusion. So we are going to start with the first premise, P implies Q. Okay, and P implies Q is the same as not Q implies not P. This was one of the rules of inferences that we had seen for conditional statements. Look at the logically equivalent statements of conditional statements. Okay, so we had seen that P implies Q is equivalent to not Q implies not P. Okay, so using that, we convert the first premise to not Q implies not P. Then we take the second premise. The second premise was not P implies R. Okay, so now we take not P implies R, and using these two premises, not Q implies not P and not P implies R, you can see it is of the form P implies Q, Q implies R, therefore P implies R. So we have from hypothetical syllogism, not Q implies R. That is what I have shown over here. P implies Q is true, Q implies R is true, then P implies R should also be true. So we have now not Q implies R is true by hypothetical syllogism. Now let's look at, the third premise. Third premise was R implies S. Again, we have the form P implies Q, Q implies R, so P implies R. Again, use hypothetical syllogism, we get not Q implies S. Okay, and not Q implies S is our conclusion here. Not Q implies S. So, these premises do lead to the conclusion that not Q to the conclusion. Therefore, we have a valid argument for that conclusion. Okay, now let's look at resolution. Okay, we've already looked at resolution. See, this was resolution. P or Q and not P or R implies Q or R, because if P is true, then not P is false. So both of them cannot be 1. Then the only option is Q is 1 and R is 1. Okay, so Q and so or R is equal to, is implied from these two statements if they are to be true. Okay, so remember what is resolution. First, computer programs have been developed to automate the task of reasoning and proving theorems. Most of the programs use rules of inferences known as resolution. So for automating of theorem proving, resolution is the rule of inference that is used mostly. Okay, and most rules of inferences are based on tautology. That means if two statements are true, then the conclusion should also be true. It should be tautology. The final disjunction, see, this is a disjunction, P or Q, and this is another disjunction, not P or R. Okay, and the rule of inference is the conjunction of two disjunctions, which implies another disjunction. That resultant disjunction is called the resolvent. So Q, in this statement, Q or R is called the resolvent. Okay, let's look at an example. Use resolution to show that the hypothesis Jasmine is skiing or it is not snowing, and it is snowing or Bart is playing hockey imply that Jasmine is skiing or Bart is playing hockey. Okay, so we have two premises and one conclusion. Let's look at, first create the propositional statements. Jasmine is, let P be Jasmine is, or in this case here it is written as it is snowing, because in both statements there are it is snowing. Let P be it is snowing. Let Q be Jasmine is skiing, and let R be Bart is playing hockey. Okay, now the first statement becomes not P or Q. The order does not matter because it is or. Okay, and the second statement becomes, premise becomes P or R respectively. Okay, so now we have two premises, one of the form P or R and the other is not P or Q. Now this is in the form of the resolution. Okay, so we leave out P and not P, and we have Q or R, which is Jasmine is skiing or Bart is playing hockey. Okay, so the argument is valid and the conclusion follows. Okay, another example, show that the premises P and Q or R and R implies S implies the conclusion P or S. First, let's rewrite the premise. Okay, when we rewrite the premise, we get here P or R and Q or R. Okay, now if this statement should be true, okay, we rewrote this statement with an equivalent statement. Now, if this statement should be true, then both P or R and Q or R must be true. Okay, so both these statements should be having the value 1. Fine. So now let's take this just one part, P or, because we are interested in P or S. Okay, so here we don't have P, so we are leaving out this part. This is also 1 and this is also 1. We are taking this section of the first premise, P or R, and take the next clause, R implies S. Okay, now R implies S is equivalent to not R or S. Remember, P implies Q is equivalent to not P or Q. So using that statement, this implication or conditional statement can be converted to not R or S. So now we have got P or R and not R or S. So leave out the R and the not R, we have got P or S, which is the resolution form. So again, the conclusion is valid because the statements are in a valid form. Okay. Now let's look at fallacies. Wrong arguments or incorrect arguments, invalid arguments are called fallacies. Okay. And many times theorems go wrong because the arguments are wrong or fallacies are employed. And some of the common fallacies we are just going to look at. Fallacies resemble rules of inference, but the form that has been used is incorrect. Okay, and these are based on the actual rules of inferences were based on tautologies. That is, when one statement is true and another statement is true, then the conclusion is true. That is how we had done rules of inferences. Okay, but fallacies are based on contingencies, not tautologies. Now, what was a contingency? If you remember, we had told earlier, when a particular statement is always true, it is a tautology. And when a particular statement is always false, it is a contradiction. When a particular statement is neither always true nor always false, then it becomes a contingency. So rules of inferences are true, fallacies are true sometimes and false sometimes. Those kind of statements cannot be taken as rules of inferences or correct arguments, valid arguments. Okay, so let's look at an example between correct reasoning and incorrect reasoning. The proposition P implies Q and Q, it implies P. Okay, our actual modus ponens was P implies Q and P, it implies Q. This is not of that form. Please see very carefully that this is not of that form. Okay, it is not P implies Q and P implies, that is concludes Q. Okay, they have changed the order of the values. This is no longer a tautology. So the format or the form is not modus ponens. Okay, so this is not a valid argument, and therefore the conclusion cannot be a valid conclusion. And this kind of reasoning is called fallacy of affirmation. Okay, this kind of reasoning is called fallacy of affirmation. Okay, it is affirming the conclusion by a false premise. Is the following argument valid? If we do we are looking at examples of fallacy of affirming the conclusion. Okay, let me just underline that. Called fallacy of affirming the conclusion. Okay, let's look at an example. Is the following argument valid? If you do every problem in this book, then you will learn discrete mathematics. You learned discrete mathematics. Therefore, you did every problem in this book. There are two premises. If you do every problem in this book, then you will learn discrete mathematics. Second premise is you learned discrete mathematics. And the conclusion is you did every problem in this book. So let P be you, because the commonality is you did every problem in this book. Let P be you did every problem in this book. Let Q be you learned discrete mathematics. Then we have two arguments. One, P implies Q, and the second argument you learned discrete mathematics is Q, and the conclusion is supposedly P. But this is not of a valid rule of inference format or argument form. Okay, this is not modus ponens. Modus ponens was what? P implies Q and P. Here it is not P, here it is Q. So it does not imply P. This is fallacy of affirming the conclusion. So the conclusion does not follow. It is a fallacy. Okay, the proposition is not, sorry, another fallacy. We're looking at another fallacy. P implies Q and not P implies not Q. Okay, this is actually a distortion of modus tollens, where we had not P and let's just go back to modus tollens. Here, modus tollens, we had not Q and P implies Q. Okay, what did we have? This implication part was a not over here. Then it had implied not P. So let's come back. See over here. Here we have, it was supposed to be not Q and P implies Q implies not P. Okay, but here it is not P and P implies Q, and they are saying that it implies not Q. Okay, it is a distortion of modus tollens. It is not a tautology. So that means it is a fallacy. Okay, and this kind of fallacy is called fallacy of denying the hypothesis. Okay, so it is an incorrect argument form. Okay, so this is called the fallacy of denying the hypothesis. Let's look at an example. Let P and Q, okay, we are looking at this same argument, discrete mathematics. If you do every problem in this book, then you will learn discrete mathematics. So P is you did every problem in this book, and Q is you learned discrete mathematics. Okay, so P is you did every problem in this book, Q is you learned discrete mathematics. If the conditional statement P implies Q is true and not P, you did not do every problem in this book is true, is it correct to conclude that you did not learn discrete mathematics? In other words, is it correct to assume that you did not learn discrete mathematics if you did not do every problem in the book? Okay, and we are making the first premise is that if you do every problem in the book, you have learned discrete mathematics. Okay, even though these individual statements are true, it is not of a valid argument form. This is fallacy of denying the hypothesis. So the conclusion that you have not learned discrete mathematics because you have not done, all the problems in the book is not true. It is not a valid uh, argument. Okay, so this is an example of fallacy of denying the hypothesis. Now we are coming to the last topic of today's lesson, rules of inferences for quantified statements. Okay, we have four rules of inferences for quantified statements. One is universal instantiation, the other is universal generalization, and then we have existential instantiation and existential generalization. Okay, now what is universal instantiation? Universal instantiation is the rule of inference used to conclude that P of C is true where C is a particular member of the domain given that for all x, Px is true. Okay, now just think about it. If we have an instance of a universal quantifier, okay, which is true, then we can conclude that the instantiation is true because what is the universal quantifier? For all x, Px is true. In that case, if we take one element of this domain x, which is C, then that Pc will be true. Okay, so that is, we are taking an instance and saying that it is true because the universal rule or quantifier statement is true. Like, for example, universal instantiation is used when we conclude from the statement, all women are wise. This is for all x, Px. Okay. And we are concluding that Lisa is wise because Lisa is an instance of woman. And if all women are wise, then Lisa should be wise. This is a valid argument. So, universal instantiation is a valid rule of inference. Then we have universal generalization. Okay, this is the rule of inference that states that for all x, P of x is true, given the premise that P of C is true for all elements C in the domain. Okay, that is, we are saying that if we have the generalization for all x, P of x is true, then if we take any arbitrary element from the domain x, then P of C must be true. Okay, that is what we are saying. We cannot say in the opposite direction that if one element C is true, then for all x, Px is true. No. Okay, what we are saying is if for all x, Px is true, then every element, take any arbitrary element, not a specific element, just take any arbitrary element and it should be true for this particular case. That is universal generalization, and it is used in many, you know, uh, theorems. But this can, it does not look at the last statement. Universal generalization is used implicitly in many proofs. It's not normally because it's understood that if for all x, Px is true, then every element x, for every element in that domain x, P of x will be true. It is implicit. Okay. However, the error of adding unwanted assumptions about arbitrary elements, okay, can cause incorrect reasoning. So when we take an element from the domain, it should be exactly an arbitrary element in the domain. We cannot make other assumptions on that element. Okay. Now let's look at, now since you know what is universal instantiation and what is universal generalization, this is easy. Okay. Now what is existential instantiation? It is the rule of inference that allows us to conclude that there is an element C, there is an instance of an element C in the domain for which PC is true. If there exists an X, Px is true. Okay, if there is one element where there exists X, Px is true, then there is one element. Now, this element cannot be a arbitrary element. It should be a specific element for which PC is true. So this is the difference between universal instantiation and existential instantiation. Okay. Now, existential generalization. This is the rule of inference that is used to conclude that there exists Px is true when a particular element C with PC is known to be true. Okay, so there exists Px is true if we know that there is one element C for which PC is true. Okay, this is existential instantiation and existential generalization. And this is how the rules of inference looks. For all x px, we can conclude that PC is true. Any PC is true. Okay. Now, if any arbitrary PC is true, then we can conclude for all x Px is true. This is a universal generalization. And existential instantiation is there exists Px is true. There is a PC for some element C. And if there is some element for which PC is true, then there exists X, Px is true. This is the universal instantiation and universal generalization, existential instantiation and existential generalization rules of inferences. Let's look at examples. Show that the premises everyone in this discrete mathematics class has taken a course in computer science and Marla is a student in this class implies there are two premises and it implies Marla has taken a course in computer science. Let's convert. Okay, let dx denote x is in this discrete mathematics class and let cx denote x has taken a course in computer science. So the first statement is for all x, dx implies cx. Okay, where the domain is students in the class. Then we have the next premise, Marla is a student in this class. So this is an instance of X is in this discrete mathematics class. So D Marla is the second premise. Now look at this. We have for all X, dx implies Cx and D Marla. Okay. So let's take the first premise. The first premise is for all x, dx implies cx. So this is a universal instantiation from which we can imply D Marla implies C Marla. Okay. So from the first premise and we have got the universal instantiation, we got D Marla implies C Marla. Now the second premise was D Marla. Now look at these two statements, 2 and 3. It's of the form P implies Q, P. So that was modus ponens and the conclusion is C Marla, which is the given conclusion. Therefore, this argument is valid and the conclusion is also valid. Okay, let's look at another example. Show that the premises, a student in this class has not read the book and everyone in this class passed the first exam, imply the conclusion, someone who passed the first exam has not read the book. Okay, let's convert it. Let Cx be X is in this class. Let Bx be X has not read, has read the book. We will not use negatives. Okay, we will simply represent negative as not. Okay, so has read the book, let it be Bx. And let Px be X has passed the first exam. Okay, now we can write the premises. A student in this class has not read the book is actually there exists X where CX, that is, a student is in this class and he has not passed the exam and has not read the book. So CX and not BX. And the second premise, everyone in this class passed the first exam is for all X, CX implies PX. Okay, so now we have got these two premises. We need to see whether there are valid arguments for this conclusion. Okay, let's look at the first premise. There exists CX and not BX. Using existential instantiation, we have CA or not BA. Okay, and using the simplification, P and Q implies P because only if both are 1. So CA is 1. Okay, so that means CA is true. Okay, so now from 2, using simplification, we have 3. Now let's look at the second premise. The second premise was for all X, CX implies PX. Okay, now using the second premise and universal instantiation, we have CA implies PA. Okay, now take the statements 3, which we said is true, and 5, which is implied from 4, so that is also true. 3 and 5 is of the form P and P implies Q. Okay, which is modus. Using modus ponens, we have PA is true. Okay, now from 2, just like if P and Q, P is true, then not BA should also be true. Okay, from that we have the seventh statement, again another simplification from 2, we have not BA. If PA is true and not BA is true, then PA and not BA by conjunction is true. Okay, and this is an instantiation of this particular statement. So there exists X, PX and not BX is also true from existential generalization. So we say that the argument is valid and the conclusion is also valid. Okay, now let's combine. We are not doing a lot of examples in this, just looking at what is combination of rules of inferences for propositions and quantified statements. Okay, we are combining universal instantiation and modus ponens, and it is called universal modus ponens. Okay, look at this over here. If you have for all x, px implies qx, and P of A. This is a universal instantiation, and P implies Q is the form that is used for the modus ponens. So combining modus ponens and universal instantiation, we can get the conclusion that Q of A, the instance Q of A is true. This is universal modus ponens. Similar to this, we have universal modus tollens. There we had not Q, P implies Q, concludes not P. Okay, so here we are having the universal rule, generalization for all x, Px implies Qx, and we have the instance not Qa, where Q is a particular element in the domain. If both these statements are true, then it implies not PA. And this rule of inference is called universal modus tollens. It's a combination of universal instantiation and modus tollens. Okay, let's just look at an example of universal modus ponens. Okay, assume that for all positive integers n, if n is greater than 4, then n square is less than 2 raised to n is true. Okay, use universal mode exponents to show that 100 square is less than 2 raised to 100. So let's begin. Let P of n denote n greater than 4 and Q of n denote n square less than 2 raised to n. Okay, the statement, the generalization statement is represented by for all n, P of n implies Q of n. Okay, where the domain consists of all positive integers. Assuming for all n, P of n implies Q of n, and there is an instance of P of A, P of 100, P of 100 means 100 is greater than 4. So that is true. Okay, so now we have the universal mode exponents form. So that implies that Q of A is true. Okay, so Q is n square less than 2 raised to n. So 100 square less than 2 raised to 100 is true. So using universal mode exponents, this is true. Okay, Q of 100 is true. And with this, I'm going to stop today's lesson. Up to this, you have for your series exam. Okay, proofs will be done after you come back to class. Thank you.